Welcome back. This is chapter 3 of lecture 7 in Biomedical Signal Processing. In this chapter, we will see what these Gabor functions are I have mentioned at the end of the previous chapter, and from there we will get to the wavelets and to wavelet transforms. So, what is a Gabor function? A Gabor function is a complex oscillations and it has a Gaussian window on it. So you have these complex oscillations. It has like a cosine in its real part and a sinus in its imaginary part. And on top of it there is an envelope, a Gaussian function. Here you can see the equation of it. Ht is the Gaussian window on top of it, and e to the I2p ft is the complex oscillation. So if you imagine it in 3D, then you will have a spindle. So you have this oscillation and it will have this envelope on itself. You can see it here. Now, in the previous chapters, we have seen how to use the short time Fourier transform, the windowed Fourier transform, in order to have the spectral analysis, the spectrogram. Now we will see how can we use the Gabor function. We have a signal here which we would like to analyze. It's a chirp signal, which means that it starts with a low frequency and it ends at a high frequency. So if you try to imagine it, it's something like so from a low frequency you are getting to a high frequency. And we would like to analyze this signal. You will see that there are some sudden changes in this signal, somewhere around here and somewhere around here, if you take a closer look. And these will be our basis functions. So as before with the Fourier transform, we had all the possible oscillations. In this plot, you have only 3 different basis functions, 3 different Gabor functions at different frequencies. So you have one at 20 Hertz, one at 50 Hertz, and one at 80 Hertz, but they all have the same width. So they all are between this and this 0.2 seconds long, all of them. And what we do is that we convolve our signal with these functions. So if I convolve my signal, this chirp signal, with this short oscillation, with this basis function, then I will see that it has a high similarity in the beginning and no similarity at all at the end of the signal. What does it mean? So in a convolution, if you remember, what we do is that we shift our basis function through our signal and multiply it at each possible position. And then we have different similarities. So it is like doing the transformation, calculating similarities, how similar your basis function is to your signal at different time points, like with the windowed Fourier transform. Just instead of cutting your signal, you are using convolution, which is very similar. You are just shifting this basis function through your signal and see how similar it is to your signal. And you see that this basis function at 20 Hertz is very similar to your signal in its beginning. Then the 50 Hertz is similar in the middle range, low middle range. And then the 80 Hertz is at the upper range, because we know that it's starting at 20 Hertz and it goes to 100 Hertz. But these were only 3 different basis functions. What if we tried all of them, all different possibilities of them? So this is what you have. This is the spectrogram if you try all possible frequencies. So all Gabor functions which are possible. And you will see that at different times is the frequency component of your signal. So as you are shifting through your basis functions, how well they are corresponding to that given timestamp. So you see these plots on the vertical axis in color on this plot. So if we go on to the next possibility, we again have a fixed window, so it has a fixed length, but this length is narrower, so it's a shorter window which we are using for our basis functions. And already with the convolution, you will be able to see that, okay, we had a good time resolution because we know better where this oscillation is, but you have quite a few information about this frequency. So only look at this first plot and you will see that there is one oscillation, but it would be really difficult to precisely tell its frequency. And you will see that, yes, in the convolution output, you have a smeared response to this frequency. So you don't really know what frequency is it at. And then in its spectrogram, what you will see is that, yes, it is smeared in the frequency axis, so you don't really know at what frequency that signal is happening, but you know where the change is. So here we have a very sharp response in time to that change in our spectrogram. The next possibility I would like to show you is a fixed number of cycles. So in the previous slides, we have seen fixed window lengths. One was a longer window where we had a good frequency response but bad time response. The next was a narrower window where we had a bad frequency response but a good time response. And now we will see what happens if we have a fixed number of cycles. So in the first step, you have this fixed number of oscillation, but as it is a low frequency, it will be a long window. And as you go to the higher frequencies, this number of oscillations will give you a narrow window. So what we are expecting is that here our bed resolution is not that good, but we have a good frequency resolution. And at the end of the scale, we have a very good time resolution, but a very bad frequency resolution. It will be very smeared at the end. This is what we are expecting. And this is exactly what we are seeing in our spectrogram, that at the beginning of the scale, you have exact frequency response, but this change is not that precise, so it's not that sharp where it is happening. And as you go to the higher frequencies, you will see that you have a smeared frequency response, but a very good time resolution. And this is just a shorter example where you have again a fixed window, and when you have this fixed window, then with the low frequencies you only have a couple of frequencies, and with the high frequency you have many oscillations, so it gives you a better representation of the frequency. And this is exactly what you can see, that here you have this small number of oscillations, which means that your frequency response will be quite smeared, but as you are getting to higher frequencies, it will be better, quite better. And if we are looking at this here, you see that at low frequencies, in frequency we don't really have a resolutions, because note that we had a different signal now. So if we are looking at the spectrogram of this signal, remember that in this case we had higher frequencies in the beginning of the signal and these lower frequencies at the end of the signal. So we have lower frequencies at the end of the signal, where our frequency representation is quite smeared. Here we shouldn't really care with the time resolution, and at high frequencies we don't really know what is happening. So to summarize all these informations, what you have to keep in mind that because of this time frequency uncertainty, this variation, simultaneous variation of the time resolution and the frequency resolution, you will have a fixed value. So you can imagine it as a box which have a fixed area. So if you have a low frequency resolution, a good frequency resolution, then you will have a bad time resolution, and the other way around, here you can see you have a bad frequency resolution, but you have a really good time resolution. And looking at the previous slides, you can see how these boxes are corresponding to a fixed window and to a fixed number of cycles. So, what we have done here is that we have the Gabor functions, which were these constant complex oscillations with some envelope on it, with some Gaussian window, and we have convolved our signal with this Gabor function. In wavelets, we have a so-called mother function. A mother function can be shifted, can be scaled, but it has some properties. So it's always having a zero mean. It has a finite L1 norm in the middle, and it has a unit L2 norm. So these are the properties a mother function has to fulfill. And then this mother function can be shifted, here with u, so you are shifting it at different locations, like with the convolution, when we were shifting our signal to different locations. Now we are doing this within the mother function, and you are having some scaling of it to compress it or to make it longer. And we have some normalization factor on it to have this unit norm of your mother function and all its daughter functions. So these will be your base functions in a wavelet transform. A Gabor function could be thought as a wavelet, but it doesn't fulfill all the properties required before. A Gabor function is more like a windowed Fourier transform, where the window is a Gaussian window. Because, if you remember, in the windowed Fourier transform, you are multiplying your signal with a Gaussian window, and then you are multiplying it to get the similarity with the base functions. While in the Gabor function, you are windowing your base function, your oscillation, and then multiplying that by your signal. So you are just changing the order of those operations, but it gives really the same result. A windowed Fourier transform and a Gabor function, they are just different ways of thinking about it. A wavelet transform can also be thought similarly, but it will have different base functions. So it will have the Haar functions we will learn about and other similar wavelet functions. And what we do is that in a wavelet transform, you are calculating the similarity, so you will have the multiplication, which in case of functions is an integration, and you are multiplying your signal, yt, with this mother function, with this wavelet function at a given shift and at a given scale. And that will give you the result at a given shift and scale. The scale is the frequency, which is compressing or elongating your signal, and u is the shifting of the signal, like in the convolution. So the two can be thought as the same. So this integration at different shifts is just like a convolution. And here you can see an example of that. So here is some random signal, and you can see the wavelet transform of it. You can see that at lower frequencies, Usually in a wavelet transform, we have the low frequencies at the top of the plot and the high frequencies at the bottom. So with low frequencies, you have a better frequency resolution, but you have quiet long windows. And with high frequencies, you have shorter windows, so you are better in the time resolution, but you are worse at the frequency resolution. So this is really like with the Gabor function as we have seen before. And some biomedical example for that. Here is an ECG signal, and here you can see its spectrogram, which could be analyzed using this picture. So this was chapter 3 of lecture 7. To complete this lecture, please take the quiz below, and thank you for your attention.